to select our physics. So we're actually going to use a secondary current distribution for our work. So we go ahead in here. When we choose under electrochemistry, we have primary and secondary current distribution. We have tertiary current distribution. So we go just under primary and secondary current distribution. We select the secondary current distribution. Then we go ahead to add this. Then we move to our steady, where we have to select our steady. And we'll be dealing with the time-dependent steady. So we go ahead to choose time-dependent with initialization, which we add. So this brings us to our interface, our Comsol interface, where we have added selected our physics and our steady. So we go ahead to add our parameters. We want to reload from file, programs file, Comsol, Multiphysics, applications. Then I think we can search decorative plating parameters. So when we search for decorative, it will quickly search for our parameters. Then we load it, we open, we add to our file, as you can see in here. So we've been able to load our file quickly, as shown over here. So I think we can start to build our geometry. We go to geometry, right click, then move to insert sequence, which we go ahead to add. And for our sequence, we'll be using the decorative plating geometry for our sequence. So this is our sequence that we'll be using for our work. So choosing decorative plating geometry sequence, we open, load. Okay, so now we have been able to load our sequence. Then we go ahead to build all. So that builds our geometry as shown in here. Want to show transparency as well. So as you can see in here, we go to materials. Check for materials also. We'll add our materials later, not now. So you go to secondary current distribution and you want to change the current distribution type. We maintain it as secondary for now. We'll be making some changes as well at the electrolytes. Also, we want to change the electrolyte conductivity to user defined, where we want to set this to K PPA. Here, as shown. So we want to go back to secondary current distribution. We want to add an electrode surface. where we'll add to our work. So after adding your electrode surface, you go ahead to choose the domain. So we want to select domain 4. This where we selected to be our electrode surface in here. So as you can see, there are many sections. And we have the film resistance. Now we move down to boundary condition. We have the perturbation amplitude. We have the external electric potential. We have different expressions that we can actually change them to for the boundary conditions. We have average current density, total current, and many others that we can actually change. So we are maintaining it to be the electric potential. Now for dissolving depositing species, we want to add. So we go ahead and select this area. This is where we're able to add our species. So click on to add, and it has added a species to it. So we have S1 being density as this, and molar mass as this. So we've added our dissolving depositing species to the electrode surface in here of our work. So like I said earlier on, we selected domain 4 for our electrode surface in here, and we went ahead to add the species, but we want to modify the variable for our species. We want to define it based on our parameters. So we go ahead to define it as N I. We want it to be the RO, RHO, and I. We want this to be molar mass of Ni as shown. So we go ahead to open the subdivision for electrode surface. Then we go on to check the number of participating electrons, stoichiometric coefficient for dissolving depositing species as well. We've seen that what we change when we change the variable over there, it has been defined over here. We want to change the number of participating electrons to 2. We want to change this side to 1 as well. And this is the equation that Comsol will solve it with. Goes down. Then the equilibrium potential changes to this Q on the Ni. Then move on to the electrode kinetics, where we want to choose, before that, we want to choose the local current density. So we go to electrode kinetics, then we select our expression type to Butler-Palmer equation and change this current density to this underscore nickel I and I non-nickel and I. So change the current density this side and move ahead to add to duplicate this electrode surface. We have a second. Move to the electrode reaction where we compare, but before that it has to be changed. The domain has to be changed. It has to be changed to this. That's for the second surface, and also the phase has to also change to average as shown over here. And this expression too has to change to this. As shown in here. Then move back to here and also the coefficient has to change to 1, has to be 1. So we go ahead to the electric surface and we want to add a reaction. We've added a reaction. We've added a reaction to this. Okay. So move ahead to the reaction. Then we want to move to the number of participating electrons. We will move to the potential. We also move to the kinetics. We change to cathodic. Current density has to change to this. Change this section to this. Then we go ahead to the mesh. As shown. So we want to change the element size to a final. We want to build all. Able to build. Go to our time dependence, our current distribution initialization. And we want to change this current to secondary. Then our time dependent, we want to change the output times. Let's change just this section to 60 and 600. Then we go ahead to We can study now. Compute. So we've been able to compute, then we move to our results. So we move to the selection. We want to select just a particular area, which will be the boundary. We want to select this. We want to plot to see. So that gives us the thickness change. We want to rename this plot to the projected thickness cathode. We want to duplicate this. We want to rename as the current efficiency cathode. We renamed it. We want to look at the surface and also change the expression in here to CD RLOC underscore ER1 CD.ITOT. As shown. We've changed the expression in here. Then finally plot final work as shown. So that gives us our plot for our work. Okay, so we would like to determine how to check the capacity field in a 1D battery model. So we're going to use a 1D battery model in Comsol Multiphysics to predict the capacity in the battery over a period of time and its aging over a period of time. So at the end, we should be able to plot some results showing the capacity cycle with respect to time, how it changes with respect to time, and also the state of charge as well. So we should make a plot of this as well during this study, showing the discharge curve comparison over a period of time, different cycles, and also the cell voltage during discharge for different cycle numbers. And also we should be able to make a plot of the state of charge at the separator and the electrode boundary, different cycles, the first and the last cycle for the different electrodes. And finally, show the plots of how the capacity ages or varies over a period of time. So let's get started. So at the beginning, we move to our new, go to our model wizard, then from our file, we look at our application library. So when we open our application library, it brings us to this place where we choose lithium-ion batteries and we select capacity fade. We select the capacity fade seed and we open. So when you open, it will take you to the interface and you see all everything defined, the variables. As you can see, variables have been defined over here. So it's actually inbuilt. All these things are inbuilt in the console setup, depending on the model that we are using. Go to lithium-ion battery, electrode, everything. You can see it has already been, the domain has already been selected. Open our particle electrode has actually been defined. Most of the variables have been defined. To the porous electrodes. So this is basically how it is, and if you should check the materials, you see that it's actually added materials to it. The electrolyte, negative and the positive electrode have been added to it. Go to the initial cell charge distribution. You can see everything has been input over here. So we go ahead to add the charge discharge cycling to it. That will be the first work, and we'll select our domain as form. That is all we select for this section. Discharge current, discharging current we set as -I. Minimum voltage we set as E. Maximum voltage will be max. Our charging current will be set as this. Then we check this side, which is include constant voltage charging. Then we set this side, which is the upper cutoff as charge. We would like to start, we go to the start mode, and we want to start with the charge first in this section. We move to porous electrode 1, where check to we want to add SEI as rho SEI. We want to make this here this way as our dissolving depositing species. Set it as SEI and define the density and the minimum mass as well. We go ahead to check this add volume change to, we uncheck this part. And also the film resistance, we want to change it to thickness and conductivity so that we can define the reference film thickness, which we define this way. And we also want to change the film thickness. We want to change it to total film thickness this way. Film conductivity, we want to change it to this. We move to the porous electrode reaction 1. We check everything. Then we go and we add a porous electrode reaction to the second one for porous electrode. So over here to go to the electrode kinetics. Then we make here user defined. So we can input our I. Let's go on SEI. Cycle underscore number greater than 0. this way. Move to our variables. We check to see if everything is defined. As previously, those which were in yellow are now black. Everything is now black, as you can see. Go back to porous electrode reaction 2. And we check our coefficient over here, which will make it t underscore factor -1. That is the parametric coefficient of v I theta. We go to our parameters and we check our t factor as time acceleration factor. Actually 250, yeah. So move back to our porous electrode 2 so that we can set our SEI to be t underscore factor. Our temperature should be user defined. We go on to definitions to add an integration. Where we select the negative electrode. We move to our steady. And before that, I want to show default. So we move to our current distribution initialization. We want to check if everything is in line, but first we will actually modify this part. go ahead to disable our porous electrode reaction too. So you could either click here or just disable over here. So now it's disabled. Our porous electrode reaction too. So you go to current distribution, then you go on to disable porous electrode too. Let's open this solver. On our time dependent solver, let's add a stop condition. So we want to add a stop condition to this. That cycles. And we also want to add change this part to steps before and after. So this section, we want to uncheck this part. Move to our steady. Want to uncheck generate default dot. So before you steady, you need to go to, you need to check all the areas to see whether there's no mistake, especially for the porous electrode reaction 1 and 2. So we check that it should be thing that I've done over here. Material should be graphite, equilibrium material, kinetics as well. This way carefully set it. So this was what we made some changes over here. At the equilibrium potential should be user defined, kinetics user defined. So we go ahead and compute. we have our convergence plot. So we have this. So we move on to let's close this. I want to add a 1D plot group. I want to add a 1D plot group to plot some results, which we'll name as load cycle. Name this as load cycle with the title type will be none. Plot to y-axis. Our load cycle, we want to add global. We want to input this expression I cell. So now variables I cell is already stated. Move to global. We want to duplicate this. We want to filter as well. We want to put a logical expression over here as first cycle filter. It's been stated in here. We move to global 2. And we want to delete this global 2. Just maintain this global 1 and duplicate it as well. I want to check this. I want to change this expression here to E. When we plot, this is how it should look like after plotting. We want to add 1D plot group. Change the expression to discharge. Is comparison. Our title to none. y-axis, we name it as cell potential. Want to add a global, I will name this as the first cycle. So put this expression E cell direction. Want to change, check, and make the parameter an expression. So we input our expression as T as this. This will be our expression for our parameter. And we go ahead to filter and we check this as first cycle filter charge filter. So this has to be, let's go. It's just a star over here. First cycle filter. It's a filter here. Yeah, and you're able to plot it. Move to the variables. See, first cycle spotted. Go ahead to duplicate this. How about we check the last cycle? and make this description cycle go to 200, 2000. And we go ahead to filter and make this the last. So we plot and we see last cycle for. So we make here description cycle for 1. Make the comparison a bit better. We plot. This is the first cycle, and this is the cycle for 2000 to 2000. Go ahead to add a 1D plot group. Change this to SEI, layer potential drop at 1C. Change title. Y-axis. And we change the title to this. And go ahead to label the y-axis as potential drop over let's make this potential drop over TI layer. Go ahead to add a point graph. Select what we want to check. We put our expression in here. Change your parameter to an expression. Change the expression over here to cycle number. Change the description to cycle number. Change the things to at negative electrode current lecture. We move ahead. After adding move to add a filter to it. So we label this as PCH dot filter. We'll duplicate this. In this selection, change it to here. We delete this. And here is start with the separator. To show our legends as well. We duplicate this and change this to electrolyte. While this label changes to electrolyte interaction. And go to our points of change this to yes. We change that of when you have to down plot, we have this. Plot, we have this graph. I want to add another one, the plot group, which we'll call capacity fade versus time. So capacity versus time. I'll try to be none. Y-axis show the time and base, and show relative capacity. Go ahead to add global. This becomes Q minus 1. Q score differential Q of 0. I change the parameter to expression where I name this as T pattern. Let's choose E. Description. I'll just choose time as base. Show legends to now. And we want to show this as based on calculable 18. Go ahead to add a filter to this. Yes. Charge. Filter. to duplicate this and to C one dot C underscore D which starts one change legends to nominal one to charge capacity. So we will duplicate this. Change this to this is cycle number. Change this to cycle number. Expression change to cycle number. Send this to the scene. We plot add another one electrode group. Sorry, local state of charge at separator electrode interface. This manual. Y-axis is SOC. We add a 4-point global. We add a point graph instead. So select put the expression SOC OC called surface. SOC, LOC. This is right. Make sure everything is right. Parameter expression. We choose to cdc.t underscore ch. That's we want to show our legend. So need to show this photo. It's probably let me retype this again. Make your so legends show negative electrode. So first cycle. Let's add a filter. It will be the first cycle underscore filter. We want to duplicate this point. And graph. We want to select, deselect this and select side 2, 3. This will be positive. We want to duplicate this again. And change the filter to, want to duplicate and change the filter to last. Sorry. Last. See. I want to duplicate this point you have to, and select select it's already selected, so select again here. Okay, so we have 4. 1, 2, 3, 4. Already selected. We move to want to check how variables will actually look. So in our battery, we go to how about look at porous electrode reaction. So this shows the local current density. Before that, for this I'll plot for local state of charge at separator, electrode, charge cycle, title, intention. So basically that's it. Being able to plot our graphs, and this brings us. So we start a new model where we select our space dimension. Since we'll be dealing with 3D space, select 3D. Then we go ahead to select our physics. We'll be dealing with AC, DC model, electromagnetic fields, and specifically magnetic fields, which we add. We move to our steady. We'll be dealing with stationary, so we go ahead to choose stationary. Then we're done. So it brings us to our interface. Then we can start by manually inputting our parameters. We input our parameters manually. So first we put the I now, which will be expression for our current to 5 M. So that's our current, the value of our current I'll be using. We go to our geometry. We start building. We add a work plane first. Then in the plane geometry, go ahead to add a square. Then the length of the sphere will be 0.05. The position should be minus 0.4. The YZ position should be 0.7, 0.2, sorry. Right, duplicate this, where this time around there should be minus, so we can build all, and that quickly builds two squares. So the work plane geometry, we want to add before that, let's add, we'll add the sweep, we'll add revolve to as well, but let's add the revolve in the work plane instead. So it shows the revolution angles for our two squares, as you can see. So let's build this, and this is what we can see. So build our geometry using this revolve steps, work plane, then add a revolve. Then we go back to add a sphere on the radius to be 1.3. Want to include layers, and that's 2, which should be 0.3. Go ahead to build the selected circle. So as you can see, build our circles in it. So it's quite simple building the geometry. We want to add a line segment to our work. We'll add the line segment to our work in here. We want to add sphere 9. Okay. So we select CNI in here. And over here we select CF4. Yeah. So after selecting, we want to add material. Go ahead, add material from library. And we'll add air. And we'll add a blank material as well. Want to name this blank material, label it as the coil. And it should be from 6 and 7 as highlighted, 6, 7. We want to make some little changes to the relative permittivity. Should be 1. Electrical conductivity should be predefined value. A user-defined value. Epsilon should be 1. We can add an infinite element domain now to our work. So we add an infinite element domain to our work where we want it to be on a spherical view. In here. To select domains, which will be one, we select 1, we select 2, 1, select 2, we select 8, select 9, we select 11. Basically, we select all these places, all the circle, as you can see in here. So it is 1, 2, 3, 4. Better still, let me just select everything. So up to 11, select 1 to 11. So that was what I was doing in here, selecting 1 to 11. We go to the magnetic fields. And we'll add the coil. And we also select some sections. The coil wanted to be for 7. That's what we want our coil to be. Should be for 7. Can also go ahead to select it as well. And over here we have our conductor model. Want it to be homogenized. The coil type, we want it to be circular. And we have our coil excitation from the current. Then the coil current, as we defined in our parameters, we want it to be as set in our parameters. Coil wire conductivity is predefined also in here. So if we also check the coil wire cross section area, it's also user defined. So we want to change this to either in here, that's the coil wire cross section area. So for now, let's maintain as user defined. Relative permittivity. This should be from material. Number of turns should 10. Okay. So go ahead to duplicate this. And this selection should be for 6. As you can see in here. Choose 6, that's for the second coil. Then we'll go back to the coil geometry. Want to highlight certain areas. We want to highlight certain areas in the coil for the coil geometry. We'll highlight from 25 to 49. You know what? Let me just paste the selection in here to make it simple. 25, 26, 46, and 49. These are basically the areas that we want to. Twenty-five, 26, 46, and 49. Okay, I think I'll have to do this. Okay. Let me first do this for that. Then, okay, so I have to do 25, 26, 49. So I was actually choosing the wrong section. That was square one. That's why I couldn't highlight it. Then, so after doing that for coil one, I have to do that for coil two as well. So coil two, after doing that for coil one of coil two, then I do that of coil one. So 31, 75, 72, 30. So that's for coil one. I think we're done for both coil one and coil two. The coil geometry selected all, as you can see. You can go ahead to just do the paste selection instead of going to this tedious thing. So for the coil geometry, you've seen several options in here, like the reverse direction, use robust, but we're not going to use that. So go to coil two, look at our parameters, our definitions expressed in here. Everything has been defined. Hopefully, I think we can go ahead to mesh our work. So I want to use a user controlled mesh. We have a lot of things to do. We go ahead to build the distribution. we go ahead to also build the size. I think we can add some more operations to the side. More operations. We want to add edge to our work. I think we can add an edge to our work. So our edge, we want to select want to select 40. In here. No, let's add the edge to our distribution instead. We'll add our edge rather to no, we'll first add the distribution. First add our edge, then we'll add a distribution to our edge. So the edge is where we select 40, and the distribution to is where we'll do some few editing. So modification to the number of elements, we want it to be 50. Prior to build selected. Edge 1. Okay, so I have to let me first delete this and go ahead to start the whole procedure again. So like I said earlier, we have a free triangle in here, which is actually built. So I'll start by first going back to physics control. Then I'll come to my user control. Then I come to my edge. I've selected the edge. I can go ahead to add my distribution. And this to come before my free triangle. I'll go ahead to do this. So this should be before the free triangle. That's why it actually happened that way. So I'll add a size to my free triangle, where I'll select free triangle. I'll make some selections. I'll have to, for the size of the free triangle, make some selection of, I think 6 and 5 will do. So let's make it 6 and 5. I want to make here custom maximum 12.05. Go ahead to build all. So that builds, that meshes our work, our geometry, as you can see. So you can see meshes our geometry. Move to the steady. We want to compute our work, the meshing. So we go ahead to compute. Okay. For computing, we have our magnetic flux density. We want to make a 1D plot group to select our space dimension. So this will be dealing with 1D. We select 1D. Then we add our physics. We have to select our physics. So normally to choose lithium-ion batteries, you have to select electrochemistry, come to battery interfaces and choose lithium-ion batteries. Then we add, then we move to our steady. So when we move to our steady, here we have to select the steady that we're going to do over here. So for our steady today, we'll be dealing with an AC impedance with initial values. So this brings us to our work interface. As you can see over here. So we'll be loading our parameters from a file. We'll also load our variables from a file as well. So I'll quickly take you guys through how to load the parameters and the variables from our file. So we click on parameters, as you can see over here. Then you select load from file, which brings you to the files where we have the parameters over here. So you select the one battery impedance parameters, as you can see over here. Impedance parameters. So we've actually loaded our files over here. You can see all the variables that we're using from our parameters, their value, description, and all that. So we see the thickness, negative electrode, thickness, positive electrode, thickness, separator, and many other things over here. As you can see, all these parameters or variables will be used for our model today. We go on to definitions as well to add variables where we'll load from file and we'll choose our impedance. We'll choose our impedance variables over here. So that one is impedance. So as you can see over here, our battery impedance variables. And we load all these. So kindly note that Comsol has detected some of these expressions as unknown since we've not defined them we've not yet defined some of these variables, but as we go on, all these unknown variables will be known, will be defined, and they will turn from this color to black color. So I'd like us to quickly start building our geometry. We build it using a 1D, so we can add an interval. We build by adding intervals to it. So we first build our negative side. So this is the length of the negative electrode. And we build selected. And as you can see, we've built our negative electrode, the geometry itself. So move on to add another interval for the second. We specify the coordinates as intervals, as you can see over here. And we define the left end. And we choose the length, which becomes that of the separator. Then we build. So as you can see, done that for the separator. So we continue this way to build the rest of our models. We add another interval. choose interval length. Dt plus separator plus positive field selected. There should be underscore. So we go ahead to add our materials, where we first choose our electrolyte. So we add this electrolyte. Double click to add. Afterwards, we add our 2 electrodes. Our negative electrode. Then we go on to add our positive electrode. As done over here. We close this material library so we can see our model builder clearly. So we've been able to build our geometry, we've been able to add our materials, we've been able to add our parameters, we've been able to add our variables. So we go on to add a domain point probe. Where we defined here as our reference electrode, which is RE probe. Go on to define here as so since we've chosen half of the separator, it was actually indicated over here. Open here, and we see our probe, point probe expression. So we change the variable name, and we define it this way. So we want to make this small caps. It's a bit better. So if we should go to our variables, we see that all our variables are now defined. We can go ahead now and quickly add, go to non-couplings, add integration. So we select a boundary to be at the end. For this. We choose, go to lithium-ion battery, right click, then we choose add a porous electrode. So we add our first porous electrode, but we select where it should be. We've selected that it should be at domain 1, which is the negative electrode. Go to electrode properties as well. And the electrode material should be negative, as we've indicated, clearly indicated. Move on down to check the film resistance, and we want it to be surface resistance. So we want to change the value of this film resistance to film resistance for the negative has been defined in the variable. And we want to change the electrode volume to this. We want to change this to this. Electrolyte volume fraction as well. We want to check the electrolyte conductivity and make it user defined. We want to add a correction factor as well. And the diffusion, we want to make it user defined and also make it same as well. Same as we did for the correction for electrolyte conductivity. Done same for the diffusion. We want to look at the particle intercalation as well. Look at the particle material. We should automatically be, we have to set it for the negative electrode. Initial species concentration set to we set it this way. And we set the particle mean center surface distance as this. We check the porous electrode reaction as well. Check the material, make sure it is the negative. We change the reference exchange current density as well. We add the porous mixed double layer capacitance to our porous electrode. where we change this double layer capacitance, we input that of the negative electrode. So it's for the double layer capacitance at the electrode, at the negative electrode side. We go on to add the second porous electrode, which will, since we've done that for the negative, we have to do that for the positive. As we need to change the electrode material as well. It has to be that for the positive. Do that for the film resistance, which has to be surface. Do that for positive. Change the electrode volume. Electrolyte volume as well. Change electrolyte conductivity, should be user defined. And deviation user defined should be same. Go to particle intercalation, choose our material, MCA. Select our initial species. Particle mean radius, mean center surface distance. Have to select that for the positive. Go to the porous electrode reaction as well. Our material starts with the positive. We change our kinetics. We change this to this expression. The active specific surface area has to be user defined. So we add a porous matrix double layer capacitance. L positive. Double layer capacitance is also these are defined. It's positive. Go on to add a separator. You select the domain for the separator. So our electrolyte volume fraction is epsilon separate has to be user defined. The activity has to be epsilon sep. Diffusion has to be user defined. Will be same. Yeah. Our initial values is checked. We will make some changes at the initial values, where we change some of the values in this section. So we'll first change the electrolyte potential. Also change the electrolyte salt concentration. And we want to add another initial value, which will override domain 3. So we add initial values, the second one, which will override domain 3. So we take the same value, this has to be a negative at the end. This goes to initial, this goes to We want to add electric ground to it. It should be at this first point. We want to add an electric potential as well, which will be at the end. This. Which we want to define as this. We want to add harmonic perturbation to our electric potential. We'll define here as we want to add additional porous electrode material as well. It should be that for our positive, as we've selected here. The input here. We click on the porous electrode reaction. And we want to disable this part. And afterwards, we want to add a porous double layer capacitance to this effect. We want to change this to 1. We want to set this to a user defined. S OS 1. So just have to make sure all your expressions are named correctly. We go to our mesh where we use a user controlled mesh. For our work, go to the first size. And we want to custom it. We want to set here as 1. going to go to size 1. We want to select just 2 and 3 for this. I want the maximum element size to be 1. Secondly, set the far end, include the far end, in the custom set this as 5. Set as 5, set for 27 to see how it will work. So we uncheck this and this. We go to our frequency domain perturbation. We put our range. This way. Okay, so you notice there was an error. That means we typed place wrong at this should be at this end. Should be this. So we can go ahead and compute and define. Good to go. So it has actually worked now. We've actually been able to compute our work. Now we move to steady. Then we want to open our solver. Look at this solver. Solution solver. I want to copy the solution. I want to copy the solution. And we want to paste. Now that we've copied, we have to, so we are going to paste it. So we first name this one not optimized. And we'll paste this, the one I've copied it, in a different section. add a table. We want to name this as experimental impedance table, which we will actually import. It's a CSV file. You can see over here. We have experimental data over here, and we would like to name this as a reference electrode. Probe table. We move to probe plots group 1. We want to name this as reference electrode RE. We want to add a 1D plots group as well, which will label as the Nyquist plots. Label this as the Nyquist plots. We want to change our data sets to a different one. We want to use the not optimized solution. We want to change the title to none. Let's check y and x axis, which is very important. Want to use omega this. We want to paste this here, but we'll change this to imaginary. So that's brackets. So now Nyquist, we want to add a point graph, which you select for. You can actually click here to paste. is the same. Now expression will be imaginary C ground. It's giving us the units automatically. Parameter, we want an expression. We want the real C ground. Which we should date. We have our plots here. Coloring. Line is solid. Let's make it 2. Show our legends. Let's input manual. Show. Call this cell impedance. How about that? We will duplicate this as well. The label will be impedance for NCE versus reference. Okay. Over here, we change our expression. We make here B should be reference of NCE. The expression down here should be the same. As we've done over here. So we have real zero reference NCE, imaginary zero reference NCE. Take this to name our legend. And we have our plots. We go on to make a duplicate of the same work. And we add we want to make this LTO versus reference. So in here, change this to LTO. So for our expression for the Z, we use LTO. So we use LTO. This as LTO. It's plotted here, as you can see. We move to our Nyquist plots, where we want to add a table graph. Table graph, we select it as experimental, impedance, and versus reference. Our table, we want to select the experimental impedance table. Our x-axis. So this is our experiment impedance table, the one we imported. Our x-axis, column 2. Note column should be manual. So this is actually column 2 is always real, and column 3 is imaginary. Go to legends, where we want to show our legends. I want to name this as experimental NCA. So it's plotted in our graph, as you can see. Experimental impedance NCA. Legend, we want it to be upper left this way. Want to preserve the aspect ratio. We want to plot as you can see. We want to conduct a parametric sweep. Go to study 1. The parametric sweep. And how about the load from a file? Load from a file. Load from the file here. And we choose the impedance parametric sweep. to see how the values will be. You need to study to see, to compute and see. We go to parametric solutions 3. We want to make it parametric sweep. We want to put a Nyquist plot. We want to duplicate. We want to change the duplicated one to a Nyquist plot parametric sweep. We look at the impedance this side, and we want to change data sets from here to parametric sweep. We want to change the legends to as well to reference original settings. We want to input these. CDL plus so minus 2. So positive 1. So, oh, so, we have this minus 3. this should be okay, this should be our film -5. Use this to that and to omega m and side omega m this is this out plus 4 10 -7 okay, 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 right. Go to the point graph and you want to disable this point graph impedance. You want to disable the impedance for that, so we can see our plot. Now we go on to add physics so that we can add optimization. We add a general optimization to our work. Let me close this side. We want to add a global least square objective. So after adding our global least square objective, we want to browse and load our experimental file. So we've added our experimental data. If you have any experimental data, you could actually use it as well. We want to add a parameter column to this, which you want to define as frequency. So that's the parameter column 1, that's the frequency. We want to add a value column. So this value column will give us this expression. Which ones? Let's go AC. Let's name this as the real impedance. To name this as e to 6. Move to the value. We want to duplicate this. We want to make this imaginary. This also becomes imaginary. So we have the real and we have the imaginary. We want to add a steady. Which is within lithium-ion battery. We want to choose an AC impedance. So we move to steady 2. We uncheck these two. So under steady 2, we want to add an optimization. We want to use this type for our method, SNOPT for our method. This actually increase the tolerance, reduce the tolerance, and the least square frequency, let's make it from the least square frequency instead. So we've actually made this from the least square. Down, and we want to set our control variables and parameters. We want to set that for the I naught positive exchange current density. From thickness of the positive and we will then set the initial value for this. It will make set as 1 exponent -3. This will be 1 exponent -3. We add, that will be the CDL positive double layer capacitance for the positive. We add another, that will be CDL underscore volume of positive capacitance, volumetric capacitance. Here we set as 0.5. Here we set as 5. 1 exponent 5. I like to expand this properly. So we want to set this upper bound 1 to 6. We want to set this to 1 exponent -6. So 5 exponent -3. 0.1 1 exponent 5. Let's set here to be 0.9. Let's set here to be 1 exponent 6. So after setting, we move down, then we go to output while solving. While solving, we plot the default to steady to. We want to show default solver. optimization solver. Want to make this the gradient method as numeric. We set intervals 5 exponent -4. 3. This section. Go to our definitions, and we want to add global variable probe. So name this as exchange and to input this positive. Want to set the output table. Want it to be same as the and it should be on input 1. Want tables, want to add a table. Want to name this table as optimized. Parameters table. Exchange current density output table. Want optimized parameters. We want to duplicate this and name this as the double layer capacitance. We want to duplicate this as well. We want to name this as a film resistance. Let's see. The film want to duplicate this as well. This will be the parametric double layer capacity plus electronic So next, we want to also duplicate our next plot. This duplicate should be next plot optimized data, so it should be none for now. Should be steady 2. So no, this should actually be for it shouldn't be here, it should be for here. So here should actually maintain. Here should actually maintain. So these changes, the data set should maintain. However, that for the next optimization is what we have to change. So go to the next optimization, then this is when we change this over here, as you can see. Go down, then marker should be set as square. It should be in data points as well. All these will have to go to simulated impedance NCA versus reference. Okay. Experimental. We want our marker to be square. Go to steady optimization. Now output while solving, we want it to be at the next plot optimization. That's where we want our output should be. So we go ahead and compute. Wait while it computes. So simulated low and okay. Okay. So as you can see, our simulated impedance is our experiment. That's our experimental impedance, and we've actually optimized our simulated impedance to actually meet our experimental values. So if you should go to okay. Okay. Move to about 10 and let's change this to optimized. We've seen our results being plotted. So this is how we do optimization for our Nyquist plots, and this is a Nyquist plot, an optimized Nyquist plot. The results supposed to add 1D plots. After adding, I have to add a line graph instead. So not a point graph, line graph instead. So select 50, 40. Then I go ahead to plot, and that gives us a plot of the magnetic flux density against the arc length. So that brings us to the end of our work. And thank you for following to the end. And if you have any question, kindly drop them in the comment section. If you would like to suggest some videos you'd like me to post or produce, I would actually look up to them and create them. So see you in the next video. Don't forget to like this video. Goodbye. At the end, we should produce these results, these plots, and see how the effect of these multiple intercalating materials will be. So I think we can get started now. So we start by going to our model wizard, where we choose our space, working with the 1D space. So we choose 1D. Then we select our physics. So we want to use lithium-ion batteries. So we click on electrochemistry, and we look for battery interfaces where we select lithium-ion batteries. Then we move to our study. We'll be dealing with time dependent with initialization. So we add to click our study. Done. It brings us to our interface, as you can see. So we look at our parameters and we want to load our parameters. Go programs files, Comsol files. Batteries. So we will be looking at choosing parameters from here. So when you go to your programs files, applications, battery, fuel cells, lithium ion battery, to bring it to this section where you have to load your parameters over here. And you can see we have several parameters that you can work with. There are several parameters over here that has been inbuilt in the Comsol setup, as you can see over here. So we will be looking at the battery, the parameters that we're working with is right over here. We're looking at battery multiple materials parameters, as you can see over here, and we load it. So it brings us here. And when you load it, you get all these parameters over here. So this is what we'll be working with right here for work today. We can go ahead to build our geometry. We add an interval, specify the interval, make it interval length, and we input what the length will be. We want to use LNEG, LSEP. We want to add L positive. Afterwards, we build the selected, and it's been built over here. So afterwards, we can go ahead and add our material. We add from library. We choose our electrolytes first. Then afterwards, we add our electrode that will be dealing with. After adding your negative, you have to add your positive electrode too. So add our MO electrode too as well. And we close this material section. So as you can see, we have two positives and one negative. We'll look at the NCA, look at the basic equilibrium, and we look at the interpolation. Let's see how it looks. As you can see, and we will also look for that of LMO, look at the basics, look at the interpolation, and we plot to see the difference. See, there's a huge difference between that. Go on to add our variables, which will load from our file. We load from our file right here, multiple materials variables. As shown here. So these are the variables that we will be working with in our work for today. So it's very easy to locate where your variables will be if you follow what I'm doing exactly. We go to lithium and want to add a porous electrode to our work, and we select the domain, which is the first domain. We go on to choose, we look at the, before that, let's open our material section, then to close the side. So at the porous electrode, we go down and we define the electrode material. So we look at the electrode material here, and we want it to be, if chosen here, so we want it to be the negative electrode, because this domain already is indicated as a negative. And we look at the porous matrix. We want to define this, and you see it's Comsol has detected it as an unknown variable, as you can see over here. But later on, as we move on, it will be defined. Go to the particle intercalation. Very important, we select the material, which is a negative. We go to particle transport properties, where we look at the species concentration transport. We want to change this to the selection in here. Then we look at the particle mean center surface. We should use that of the negative. Look at particle discretization. We want to change the number of elements. We want to make it 20. In this section. You look at the distribution, and we want to make it linear at the particle discretization. And we quickly move to the porous electrode reaction. We look at the material. We choose negative. We look at the reference exchange current density. Choose this. Specify this. Go to lithium. I want to add another porous electrode. We select the domain. We select the electrode material, which is the positive NCA. We change this electrode volume fraction as NCA. Change this to X. We go to effective transport parameter. Make this user defined. Correction factor should be this. Positive. And that of diffusion 2 has to be user defined. and the same for same as this. So we did copy and paste over here. So we move to the particle intercalation. We choose our material. Select our material to be NCA. Move to our particle mean center surface, which we change to RP positive of CA. And we change the species fixed or to Baker. We did change it to Baker. So we change this to this. And we go to porous electrode. We change the material to NCA. We change the exchange current density. Oh. All should be in small caps. Then NCA in big caps. It's small caps. Right. Okay. We go on to add an additional porous electrode material. We select the domain. Then the volume fraction too has to be changed. Like this. Add the particle intercalation. And particle transport species as this. Concentration. We want to change this to solid phase concentration. Defined in here. We go to the porous electrode reaction one, then we want to define the material. We define the material. You have to select the material for this. So our material is positive. Also, you have to change this extreme current density to this, and we change the concentration to insertion concentration. Okay, so some input just the small caps has to be small caps I. So we go on to add separator, which will select the domain. Separator is this section, and we replace the volume fraction set. Then electrolyte conductivity is user defined. As you can see, also copy this, same for the diffusion, has to be user defined. So we place this in here. So we go on to add initial charge distribution, the initial cell charge distribution. We want to make this section, the initial charge, battery cell setting as state of charge. And we input this values as SOC underscore cell. Yeah. And this section is also underscore there. No, this is but we move to the negative electrode selection, and obviously we have to select this section for it, that because that's a negative domain, and also do that for the positive, select the section. So after doing this, we go on to check where our value was in it's still unknown. It's because of this should be underscore and it should be correctly named. So now that all our variables are, you go on to add an electric ground. Want to add an electric ground. We select a section. So it's this point that becomes our electric ground. Then we go on to add an electrode current. Add an electrode current to this as well, which we select where to be at the fourth. Go to defaults and we want to click here and make our temperature T. We set it to T. We go on to mesh. We want, let's make it fine. Let's build. Okay. Let's go on to add an integration. Then we select boundary for this integration. We want it to be so it's fourth. Let's name this integration as, we set the operator name to be a different name over here. How about we name it as end terminal? So we set that section. How about we move to the current and we go to the time dependent and we change to 0 to 3, 6. We go ahead to show our default solver. And our time dependent solver. How about we change the times to store as this? And we go on to add a stop condition. We add our stop, our expression. So this will be our stop expression. So our output at stop, we want to deselect and check this. And we want to uncheck the default plots. And we go ahead to compute. Okay. So we've been able to compute this. It has given us some results. We want to add a 1D plot group. Where we want to name this plot group as constant. Discharge. We want to add a point graph to this. Choose to end. We make a selection. If actually can actually paste this and will actually be the same. I can use this paste selection to paste it. Right, you can just click on it and good to go. We select the expression over here. Go to our lithium-ion batteries. This is our expression that we should be using. Electric potential. When we plot it, gives us electric potential versus time graph of it. You can look at the plot settings. To check and change what should be at the y and x axis. On the y axis should be the voltage. The title we want it to be this. We want to make some edit the axis. Three. So, as you can see, so you go on to add another plot group. We are the 1D plot group. We want to name this as surface concentration positive. And we'll add a point graph. We will select this and go on to choose particle intercalation. Then is the after solid phase we have insertion, and insertion particle concentration surface. Legends we want to name this as NCN. We want to plot this. So we have our plots here. We want to duplicate this point graph. Want to change the expression over here. We want to select the insertion particle concentration. So we have our insertion particle concentration. This is what we'll actually select for our work. So we just double click on it. It gives us this. Or you can just type this expression over here and that will give you the same results. So we have our plots being done. We go on to the surface. Title, we want to name the title as want to name the y-axis as surface concentration. To do some editing of the y and x-axis. Okay, so we plot this. We've seen some changes. We want to change the position of the legend over here to upper left. As you can see. So we go on to our steady solution. We want to duplicate our steady solution one. We want to name this as, we'll change this here to take the component from this first section. Material tool has been changed. Go to our results. We want to add a 1D plot group. We want to make this a particle concentration. Negative. We change the data sets to this. We do our time selection as interpolated. We need to add a range. To start from 0, step 200, stop at 2000. We want to add this to this. We want to add another range to as well. We want to start at 2032. Step will be 2030. Then 2200. Let's add it. No, we make this 2030 instead. We add another range. And this would be so if inserted or added our time range. We want to add a line graph to this. So we select one. Can also click here to select all, and we have to put our expression for this, which will be oh, so we want to plot this, and here we have our plot. Let's check the x-axis. Name this as normalized particle dimension. We check this as well. We want this to be the particle concentration. And we want the title to be this. We add another steady. We go ahead to add a steady for this. Then we choose a time dependent with initialization. Steady 2, we want to change here to 0 to 600. We want to add the parametric sweep to this. We'll add the parameter for which we want to check it. So we choose this and we try to vary within these parameters. go on to steady. We want to show the default solver. We go to solver 3. We want to see the time dependent solver, where we want to make the output times steps taken by solver. How about after that we add a stop condition. We input the expression, which will just be the same as, sorry, this expression. So you can copy and paste, but I'll type it again. Stop. 1 dots and that's the expression. Stop expression. We want to uncheck this. Add 1 inside. Okay. We want to also uncheck our default plots and begin to compute to get our results. We begin seeing some results. So we have our results. Now we go on to add a 1D plot group. We name this as voltage profiles. Voltage profiles. We'll make it parametric. We add a point graph to this. We take the data set from our parametric solutions. Highlight, select this point. Now expression will change to the electric potential. our legend, we want to show manual '95 volume 5-1 mix of NCA and LMO. (25/7) mix. That's 55/45 mix. And we have 75/25 mix of NCA and LMO. We have 525/75. Then we go ahead to plot. As you can see, we have our plot of electric potential time showing different volume mix of our electrode materials. When we go here, we want to change the y-axis to, change our y-axis here. I want to name this as just the voltage and we want to, title should be manual, because voltage profiles for different mix fractions and for NCA and NCA and O. So after that, we want to manually edit the x-axis and y-axis. Bring this to 0. Bring this to 3, and bring here to 0.2. We plot. Okay, so now it makes it more better. Then we want to change our legend position to the lower left. You can see over here. So we've been able to see how mixing different positive electrode materials will have on the voltage on the battery during a period of time, and we've been able to plot these voltage profiles for different mixed fractions of NCA and LMO. Also made a surface concentration plots for the NCA and LMO electrode materials. Also, we're able to do some parametric study on how these different mixed fractions will have on the voltage over a period of time in the battery. So I'm glad we're able to produce these plots in this work that we did today. Okay, so thank you for your attention. So at the beginning, we move to our new Go to our model wizard. Then from our file, look at our application library. So when we open our application library, it brings us to this place where we choose lithium-ion batteries and we select capacity fade. We select the capacity fade C. We open. So when you open, it will take you to the interface and you see all everything defined, the variables. As you can see, variables have been defined over here. So it's actually inbuilt. All these things are inbuilt in the console setup, depending on the model that we are using. Go to lithium-ion battery, electrode, everything. You can see it has already been, the domain has already been selected. Open our particle electrode has actually been defined. Most of the variables have been defined. To the porous electrodes. So this is basically how it is, and if you should check the materials, you see that it's actually added materials to it. The electrolyte, negative and the positive electrode have been added to it. Go to the initial cell charge distribution. You can see everything has been input over here. So we go ahead to add the charge discharge cycling to it. That will be the first work, and we'll select our domain as form. That is all we select for this section. Discharge current, discharging current we set as minus I. Minimum voltage we set as E. 1 voltage will be max. Our charging current will be set as this. Then we check this side, which is include constant voltage charging. And we set this side, which is the upper cutoff, as charge. We would like to start, we go to the start mode, and we want to start with the charge first in this section. We move to porous electrode 1, where check to we want to add SEI as rho SEI. We want to make this here this way. As our dissolving depositing species. We set it as SEI, and we define the density and the molar mass as well. We go ahead to check this add volume change to, we uncheck this part. And also the film resistance, we want to change it to thickness and conductivity, so that we can define the reference film thickness, which we define this way. And we also want to change the film thickness. We want to change it to total film thickness this way. Film conductivity, we want to change it to this. Move to the porous electrode reaction 1. We check everything. Then we go and we add a porous electrode reaction to the second one for porous electrode. So over here to go to the electrode kinetics. Then we make here user defined, so we can input our I. Let's go on SEI. Cycle. And let's go on number greater than 0. This way. Move to our variables. we check to see if everything is defined. As previously, those which were in yellow are now black. Everything is now black, as you can see. Go back to porous electrode reaction 2. And we check our coefficient over here, which will make it T underscore factor -1. That is geometric coefficient of V I theta. We go to our parameters and we check our T factor, that's time acceleration factor. Okay, 250, yeah. So move back to our porous electrode 2 so that we can set our SEI to be T underscore factor. Our temperature should be user defined. We go on to definitions to add an integration. Where we select the negative electrode. We move to our steady. And before that, I want to show default. So we move to our current distribution initialization. We want to check if everything is line, but first we will actually modify this part and go ahead to disable our porous electrode reaction 2. So you could either click here or just disable over here. So now it's disabled. Our porous electrode reaction to. So you go to current distribution, then you go on to disable porous electrode 2. Let's open this solver on our time dependent solver. Let's add a stop condition. So we want to add a stop condition to this. That cycles. And we also want to add changes part to steps before and after. So this section, we want to uncheck this part. Move to our steady. Want to uncheck generate default thoughts. So before you study, you need to go to, you need to check all the areas to see whether there's no mistake, especially for the porous electrode reaction 1 and 2. So we check that it should be thing that I've done over here. Material should be graphite, equilibrium material, kinetics as well. This way, carefully set it. So this was what we made some changes over here. At the equilibrium potential should be user defined, kinetics user defined. So we go ahead and compute. we have our convergence plot. So we have this. So we move on to let's close this. I want to add one B plot group. I want to add a one B plot group to plot some results, which we'll name as load cycle. Name this as load cycle with the title type will be none. Plot to y-axis. Our load cycle, we want to add global. We want to input this expression I cell. So now variables I cell is already stated. Move to global. We want to duplicate this. We want to filter as well. We want to put a logical expression over here as first cycle filter. It's been stated in here. We move to global 2. And we want to delete this global 2. Just maintain this global 1 and duplicate it as well. I want to check this. I want to change this expression here to E. When we plot, this is how it should look like after plotting. We want to add one the plot group. Change the expression to discharge. Is comparison. A title to none. y-axis. We name it as cell potential. Want to add a global. We will name this as the first cycle. We put this expression in cell. Direction. Want to change, check, and make the parameter an expression. So we input our expression as T as this. This will be our expression for our parameter. And we go ahead to filter and we check this as first cycle filter charge filter. So this has to be, let's go. It's just a star over here. First cycle filter. It's a filter here. Yeah, and you're able to plot it. Move to the variables. See, first cycle plotted. Go ahead to duplicate this. How about we check the last cycle? and make this description cycle go to 200, 2000. And we go ahead to filter and make this the last. So we plot and we see that's the cycle for. So we make here description cycle for 1. Make the comparison a bit better. We plot. This is the first cycle, and this is the cycle for 2000 to 2000. Go ahead to add a 1D plot group. Change this to SEI, layer potential drop at 1C. Change title. Y-axis. And change the title to this. And go ahead to label the y-axis as potential drop over let's make this potential drop over CI layer. Go ahead to add a point graph. Select what we want to check. We put our expression in here. Change your parameter to an expression. Change the expression over here to cycle number. Change the description to cycle number. Change the things to at negative electrode current collector. We move ahead after adding move to add a filter to it. So we label this as PCH dot filter. We'll duplicate this. In this selection, change it to here. We delete this. And here is that of the separator. To show our legends as well. We duplicate this and change this to electrolyte. While this label changes to electrolyte fraction. And go to our points of where we change this to yes. We change that of when you have to down one plot, we have this. Plot, we have this graph. I want to add another one, the plot group. Which we'll call capacity fade versus time. So capacity versus time. I'll try to be none. Y-axis show the time and days. Then show relative capacity. Go ahead to add global. This becomes Q minus 1. Q score differential Q of 0. Change the parameter to expression where I name this as T pattern. Let's choose T. Description. I'll just choose time as is. We show legends to now. And we want to show this as based on calculable 18. Go ahead to add a filter to this. Name as charge filter. Want to duplicate this and to C1 dot T underscore D which starts one change your legends to nominal one charge capacity. So we will duplicate this. Change this to this is cycle number. Change this to cycle number. Expression change to cycle number. Send this to the scene. Plot add another one deplot group. Sorry, local state of charge at separator electrode interface. This manual. Y-axis is SOC. We add a 4-point global. We add a point graph instead. So select put the expression SOC OC porous surface. SOC, LOC. This is right. Make sure everything is right. Parameter expression. We choose to cdc.t underscore ch. But we want to show our legend. So need to show this photo. It's probably let me retype this again. Make your so legends show negative electrode to first cycle. Let's add a filter. It will be the first cycle underscore filter. We want to duplicate this point. And graph. We want to select, deselect this and select side 2, 3. This will be positive. We want to duplicate this again. And change the filter to, want to duplicate and change the filter to last. Sorry. Last. See. I want to duplicate this point graph 2 and select it's already selected, so select again here. Okay, so we have 4. 1, 2, 3, 4. Already selected. We move to, want to check how variables will actually look. So in our battery, we go to how about look at porous electrode reaction. So this shows the local current density. Before that, for this I'll plot for our local state of charge at separator, electrode charge cycle. Try to attention. So basically that's it. Being able to plot our graphs, and this brings us. In this section, we'll be looking at how to use Comsol to check the corrosion and the deposit for a cathode and a anode material. So we'll draw our geometry indicating for with both anode and cathode, we use this geometry, one side to represent the anode and another side to represent the cathode. And we are going to illustrate how the stress corrosion cracking will occur under the geometry. So at the end, we should be able to plot the local current density over a period of time, and also we should also see the stress corrosion cracking results for this model. So kindly follow to the end, and if there are any questions, please let me know. And please don't forget to subscribe and like the video for me. Thank you. When we move to our model wizard, we then select our space dimension, which will be 2D. Go ahead to electrochemistry, where we want to select corrosion secondary. So we go to corrosion deformed geometry, then we select secondary, corrosion secondary to our work. So we want to add this physics to our work. This will be using a secondary current distribution. Move to our steady. where we choose a time dependent with initialization, which brings us to our interface. So quickly go to our geometry where we add a rectangle. We want to add a rectangle, and we want to draw our rectangle. 0, 1. Same here. We want to choose the position as minus 0.01. Then we go ahead to build our geometry. We go on to add another rectangle to our work, where we also make here 0.01. Our height should be this plus a little change. We want to add a little change to our work. So 1, -4. So we just want to make a little change to the height, and also to the position as well. We want to make a little change to the position as well. If you go on to build selected, as you can see. So we have built our geometry. Go ahead to booleans, and we want to make a union out of this. So we select both. We uncheck this. So we want to join these two to make it one. Those selected, and they are joined together, as you can see in here. So we can see that we've joined our two rectangles together to form a single unit. We can load our parameters from our work. We load parameters from file. We'll be using galvanic corrosion. Using galvanic corrosion, I like to search for galvanic. So these are parameters. We found it. That's galvanic corrosion with deformation, as you can see. We load our parameters. So after forming our geometry, we go on to add an electrode surface to our work. So we add an electrode surface where we select where this electrode surface will be. So we select 2 and 4 for our electrode surface. We check the species conservation. Check that Let's open to check all these sections. Okay. Then we can now go to the electrode reaction. So temperature from the model inputs, the equilibrium potential, we put in this expression. That's also our kinetic expression. We want to use a cathodic Tafel equation where we change our I not exchange current density to this, change our anodic current density to this, move forward. And we go on to add a second electrode surface. So the second electrode surface will be here. And go to the dissolving species where we add value here. We want to name this as mg. Then this is rho mg equal mg. So that's what we change in here. After we go to the electrode reaction, where we number of participating electrons, we make it 2. We set this to be 1. We set the equilibrium potential to be this. Kinetic expression is made as the anodic Tafel, which will be IO underscore. And this is anodic, which will be N as shown. Add a limiting current density, which we'll define as ILIM, anodic, as shown, as we've done in here. So that's for the electrode reaction. So we want to check what we did earlier. I want to cross check and see if actually named everything as supposed to be. Our electrolyte itself, we go to electrolyte conductivity, where we make this user defined, and this has to be sigma as shown. Go to our Multiphysics deformed geometry, check. Deformed geometry, So things set in here, geometry, deformation also sets. Move to the non-deforming boundary. For the initial, go to the second. We want to select only 5. So we want to select only 5 for this. So we want to select only 5 for the deforming electrode surface, and we want to, for the non-deforming boundary, will be the rest as shown here. So we go on to check isolation. Everything sets. Then we can proceed to check our time that we want to set. We want to set our time from 0 to 12 times 3600, and we want to end at 3 times 24 3600 as shown. This could be very clear for us. So we can go ahead and compute our work. Which generates our results as shown in here. So we've been able to generate our results as shown in here. We want to add a 1D plot group. 1D plot group to our work. Which we want to add a line graph. In our 1D plot group. So we want to select the data set from our steady solution 1. We want it from the remeshed. We want to select, as we selected our solution, steady solution 1. So view our solver. We check our meshed. Okay. So actually, we wanted to, in our time dependent, wanted to make the steady extension an automatic remeshing. So have actually gone there to do automatic remeshing and want to compute it again so that we can get that result because we need a remeshed solution. So I'm recomputing it so that we can get our remeshed solution because it's very important for our work. I just went to time dependent, came here. Okay, now so we have our remeshed results. It's very important to allow us to plot our results. So now we have our remeshed solutions. Now we go to results, we add a 1D plot group and we add a line graph. Now we can add our steady remeshed solution. So that was exactly what's needed for our work. So our time selection, we want to select from the first our work, and we want to select here. We want to select from 2, 4, and 5, 2, 4, 5, as shown in here. We want to change our expression in here to CD dot I log under ER1. That'll give us the local current density. If we should plot, this is what we have. We have in this plot. So I want us to close this space in here. Then our x-axis data wants us to change the parameter to an expression so that we can use an expression of x in here for our work. As you can see. To actually make it look this way. So we want to duplicate this work and we want to start from last. Let's plot and see. Okay. So from last, we've had our plots. We want to plot our work. So let's go ahead to open a file for this galvanic corrosion with deformation, which will open and add. We want to view as we have seen over here. So we go to want to add physics. We want to add physics to our work, new physics to our work. So we go and we add new physics to our work in here. So our physics, we come to chemical species transport. We go to transport of diluted species. We add to our work. Where we define the variables. We want this to be 2, we want our concentration to be CmG. We want this to be COH. as done in here. We want to add a moving interface. That's under mathematics. We add level sets to our work. Go to the parameters. And we want to load from file. We want to load our parameters from file, which will be under deposit corrosion parameters. We've actually added these parameters to this. Our definitions, we want to add a step to our work. Smoothing, we want our size of transition to be this. So we want to add variables which will actually load from file. We want under deposit corrosion variables. This is not defined, but later will be defined. Later be defined as we move on the course of our work. Definitions, we want to add non-couplings and general extrusion as shown in here. We want to select, we want to select a boundary for that. So select boundary. Our source frame, we want it to be this way. We want to use source map. We go to advanced and we want to set the tolerance to the closest points as much as possible. Now, general extrusion. Go to our transport of diluted species. We want to change, uncheck this convection. We want to make it migration. Move to transport properties. And we want to define the diffusion coefficient as dm on s dot bf2 plus dm e on s dot infl. And we want to also define okay, so this is one. Okay, now it's defined. The diffusion coefficient as well, DOH S dot VF2 plus DOH E LS V F1. if we start before this. We want to change the electric potential as well. We want to define it as Q. The charge number, we want it to be 2 and -1. Initial values 2 as well. We want to make here C or H4. Sorry, this is 0. As shown here. We go on to want to add reactions. We select our domain and we define a reaction should be R as delta this also is R is called OH. It's not delta. Go to our transport diluted. We want to add concentration to our work. We select boundaries and we define our species. Should be H0 as defined in here. Go to transports and we want to add, move to surface reactions, we want to add electrode surface coupling. Choose 2 and 4 for our electrode surface coupling. The reactions coefficients, we want to change this to local current density. For this, it has to be local current density. Number of participating electrons, we want 4. And so the section 2, we want it to be 4. Go on to add surface reactions, and we want to add another electrode surface coupling. So this is the second surface coupling that we're adding. We select domain 5, we go to the reactions. Same here, we choose the second region. The number we want to for this section, and we want to start from -1 in here. Close. Go to the level sets. We want to look at the level sets model. where we define the reinitialization parameter. It should be this max for as shown in here. We've defined our parameter for the reinitialization. This side, we also have to define the parameter for the controlling interface thickness, which should be LSHM. For we set the velocity field to this value. Set this to this value. This expression. Move to the initial values and we set it as the fluid 2. We want to add an inlet. The inlets we select 2, 4, and 5. And we go on to add, once we've added an inlet, we have to add an outlet. Very, very important. What's that audio? So we want to add an outlet. So after selecting our outlet, we need to select which area our outlet will be, because we've already chosen where our inlet will be. So we select our outlet, and the outlet will be the outer areas, will be from 3, 6, 7, and 1. That will be our outlet. Go to our secondary electrode. We want to define our electrolyte conductivity, add an expression to it. That will be LS dot BF2 F2 plus sigma F1 BF2 BF1 plus short linear. Go to our mesh. We want to add edit physics induced. For the first size, We want to make this calibrate for fluid dynamics, as we want to do for the first one. We want a finer one. For the second one, we want also extremely fine. We want fluid dynamics, extremely fine. Wow, work. So we move to our free triangle. We want to add, I think we have to add a size to this. Add a size to our free triangle. And there should be, for a boundary, we select 2, 5 for our boundary. Predefined should be extremely fine. Let's build and see how it looks like. So, seeing how it looks like for now. We move to 31. We want to uncheck certain areas like the deformed geometry. We want to uncheck this. We want to uncheck this as well. We want to uncheck these two. And we want to compute. Get rid of this. It should take some little time to compute. So wait patiently for it to compute. Wait a little while. Now also wait for it to compute. To take some time. To take some time. We wait a while for this to compute. Take some time. We wait a while for it to compute. We wait for some time. It's actually taking a while. It's taking a lot of time. Really sorry about that. But we can't continue unless we're done computing. So I'll plead with you that we actually wait. I'm sure yours is not also done yet. So we're almost 50% through with the computing, still computing. Patiently waits. So wait, I think we're almost done. Almost done computing. Finally, we're done. That's great. We have our results now. Took about 9 minutes. So we click on electrolyte, look at the streamline, and we want to see the positioning. We want to do a separating distance of about, let's make it about 0.035. We want to also make the range. Okay, the range is 100. We want to plot, let's see. And here we have our results. We go on to the surface to our work. We put an expression as 1 here. Then we select our coloring. We want it to be uniform. We want our coloring to be uniform. We want it to be gray as well. Go to the surface and we want to add a filter to our work. We want to name this filter as LS. That's 1 greater than equal to 0.5. That will be our filter. We want to plot our filter. So when we plot our filter, this is what we have. You can see our filter in it as shown. We want to add a 2D plot group. We want our data sets from our remeshed solution. I think, yeah, we want our data set from our, we want to select our time from about, let's say, the last time in here. This is what we want to select, and we want to go ahead and add a surface to our 2D. We want to put this expression in here, and we'll go ahead and plot. This is what we have. We go ahead and add contour to our work. Contour to, we want to change the expression in here to s dot vf1. Unit should be 1. Labels should be, we have entry, or then we have labels, total levels. So let's make our entry mode levels, and want this to be 0.5 as shown. Let's change our color table to different color. Let's say uniform. Make it black in here. And dots. So that brings us to the end of this work, and I hope we're able to plot our work, able to follow till the end. Thank you. And please kindly subscribe if you haven't, and if you have any questions, please kindly drop them in the comment sections. And don't forget to like the video. Thanks. So we start by going to our model wizard, select new, and we select our space dimension, work with the 3D, which we select. Then we come here to select our physics. So we're actually going to use a secondary current distribution for our work. So we go ahead in here, when we choose under electrochemistry, we have primary and secondary current distribution. We have tertiary current distribution. So we go just under primary and secondary current distribution, we select the secondary current distribution. Then we go ahead to add this. Then we move to our steady, where we have to select our steady. And we'll be dealing with the time dependent steady. So we go ahead to choose time dependent with initialization, which we add. So this brings us to our interface, our Comsol interface, where we have added selected our physics and our steady. So we go ahead to add our parameters. We want to reload from file, programs file, Comsol, Multiphysics, applications. Then I think we can search decorative plating parameters. So when we search for decorative, it will quickly search for our parameters. Then we load it, we open, we add to our file, as you can see in here. So we've been able to load our file quickly, as shown over here. So I think we can start to build our geometry. We go to geometry, right click, then move to insert sequence, which we go ahead to add. And for our sequence, we'll be using the decorative plating geometry for our sequence. So this is our sequence that we'll be using for our work. So choosing decorative plating geometry sequence, we open, load. Okay, so now we have been able to load our sequence. Then we go ahead to build all. So that builds our geometry as shown in here. Want to show transparency as well. So as you can see in here, we go to materials. Check for materials also. We'll add our materials later, not now. So you go to secondary current distribution and you want to change the current distribution type. We maintain it as secondary for now. We'll be making some changes as well at the electrolytes. Also, we want to change the electrolyte conductivity to user defined, where we want to set this to K PPA. Here, as shown. So we want to go back to secondary current distribution. We want to add an electrode surface where we'll add to our work. So after adding your electrode surface, you go ahead to choose the domain. So we want to select domain 4. This where we selected to be our electrode surface in here. So as you can see, there are many sections. We have the film resistance. Now we move down to boundary condition. We have the perturbation amplitude. We have the external electric potential. We have different expressions that we can actually change them to for the boundary conditions. We have average current density, total current, and many others that we can actually change. So we are maintaining it to be the electric potential. Now for dissolving depositing species, we want to add. So we go ahead and select this area. This is where we're able to add our species. So click on to add, and it has added a species to it. So we have S1 being density as this and molar mass as this. So we've added our dissolving depositing species to the electrode surface in here of our work. So like I said earlier on, we selected domain 4 for our electrode surface in here, and we went ahead to add the species, but we want to modify the variable for our species. We want to define it based on our parameters. So we go ahead to define this as Ni. We want it to be the Ro, Rho, and I. We want this to be molar mass of Ni as shown. So we go ahead to open the subdivision for electrode surface, then we go on to check the number of participating electrons, stoichiometric coefficient for dissolving depositing species as well. Seeing that what we change when we change the variable over there, it has been defined over here. We want to change the number of participating electrons to 2. We want to change this side to 1 as well. And this is the equation that Comsol will solve it with. Goes down. Then the equilibrium potential changes to this Q and the Ni. Then move on to the electrode kinetics, where we want to choose, before that, we want to choose the local current density. So we go to electrode kinetics, then we select our expression type to Butler-Palmer equation and change this current density to this underscore nickel I and I, non-nickel Ni. So we've changed the current density this side. And move ahead to duplicate this electrode surface. We have a second. Move to the electrode reaction where we compare, but before that, it has to be changed. The domain has to be changed. It has to be changed to this. That's for the second surface, and also the phase has to also change to average as shown over here. And this expression too has to change to this. As shown in here. Then move back to here and also the coefficient has to change to 1, has to be 1. So we go ahead to the electric surface and we want to add a reaction. We've added a reaction. We've added a reaction to this. Okay. So move ahead to the reaction. Then we want to move to the number of participating electrons. We will move to the potential. We also move to the kinetics. We change to cathodic. Current density has to change to this. Change this section to this. Then we go ahead to the mesh. As shown. So we want to change the element size to a final. We want to build all. Enable to build. Go to our time dependent, our current distribution initialization. And we want to change this current to secondary. Then our time dependent, we want to change the output times. Let's change just this section, 60 and 600. Then we go ahead to, we can study now, compute. So we've been able to compute, then we move to our results. So we move to the selection. We want to select just a particular area, which will be the boundary. We want to select this. We want to plot to see. So that gives us the thickness change. We want to rename this plot to the projected thickness cathode. We want to duplicate this. We want to rename as the current efficiency cathode. We renamed it. We want to look at the surface and also change the expression in here to CD ILOC underscore ER1 CD.ITOT. As shown. We've changed the expression in here. Then finally plot final work as shown. So that gives us our plot for our work.